first thing I'd like to do today is take a look at the homework and the homework answers you got from last night. There was a couple that I'm going to go over, and if you have other questions, just let me know. Let's talk about 29 while we're here. You know, yesterday we talked about how we could represent this as the magnitude times cosine of theta and the magnitude times sine of theta, and we talked about why. So in this problem, we know the magnitude was 18 and theta is 25. So we'd have to do 18 times cosine of 25 to get that horizontal component of our vector, 18 times sine of 25 to get that vertical component of our vector. And that's how 29 and 31 would have worked. Now, on some of these, we're kind of working backwards. So if they give us this linear combination form, then we would just go backwards, factor out the 7. This is 7 times cosine of this. And so we see that the magnitude is 7. The angle is 135. Okay, so let's take a look at these. If we were switching forms, we have 2 and 1, so its magnitude would be the square root of 2 squared plus 1 squared. So the magnitude is root 5. So when we're writing it as a unit vector, it is the vector over its magnitude. So we would distribute this 1 over root 5 through, and then we could switch to component form. Okay, looking at 33, we have 3 and 4, so and a magnitude of 5 here, so it hasn't been reduced at all. So how could we find that angle? So we just have this little triangle right here. We can set it up, or we could say that 3, which is our horizontal component, is equal to the magnitude times cosine of theta, and we still get cosine of theta equals 3/5. Or if we just looked at this as a right triangle, we would have gotten that same ratio. So we do inverse cosine, and in this case, we get the 53.130. All right, here is 35. So this is what we're dealing with, 3, negative 4. And so we get that magnitude of 5. So we get sine equals negative 4/5. So that would be 53.13. Now, in this case, I know that we're going all the way around here. So if that is my negative angle, it's 360 minus that. And so that gives us theta of 306.87. All right. And we already talked about number 37, so we should be good there. Okay, let's take a look at this problem. And it tells us that we have the vector -2, -5. That gives us, we can find the magnitude and direction. So the magnitude of this vector would be the square root of -2 squared, which is 4. And -5 squared, which is 25. So its magnitude is the square root of 29. So we know that -2, -5 is equal to the magnitude times cosine. So we set this up, -2 times the magnitude cosine theta. We could have also done the same thing with sine here, but chose cosine. So cosine of theta is equal to -2 over root 29. So inverse cosine gives us theta. Now, in this case, when we're thinking about this, -2, -5, we know that guy is down here in this quadrant. So I'm going to redraw this so we can just kind of think about it. We know that this vector, -2, -5, is down here in the third quadrant. But when we do inverse cosine, cosine only gives us from 0 to pi, or 0 to 180. So it gave us this. So how do we get all the way to there? Okay, so there's a couple things we could do. We could do the 360 and subtract this, because that's the same as this. And so since we know that this angle here, from here to here, is 111.8, but that's not what we want. We want all the way to here. Well, we know that this is congruent to that. So if I just subtract that from 360, I get that that direction would be 248.2 degrees. Okay, so today we're going to look at different applications. Today we're going to look at velocity in terms of its magnitude, speed, and direction. So for our first example, if I gave you the velocity of an airplane at a bearing of 65 degrees and a speed of 500 miles per hour, and we're to find that velocity, what would we do? Okay, so let's kind of draw a picture first and see what's going on here. We've got this airplane at a bearing of 65 degrees. So that's with respect to due north. So when we go 65 degrees off of that, that might take us somewhere like there. Okay, so this is our 65-degree bearing. And we know that the speed, the magnitude, is 500 miles per hour. All right, and we're going to find the vector that represents this airplane. So our airplane in this case is going in this direction. All right, so yesterday we learned we can do the magnitude times cosine of theta and the magnitude times sine of theta to come up with a component form of our vector. So in this case, we know that the magnitude, which is currently our speed, is 500 miles per hour, and cosine of theta. Okay, now our bearing is 65, but that's not the theta we're looking for. When we talk about cosine, we're talking about this angle. So if this is 65, what is this? 25. So this is where we have to be a little careful on these problems. And so this would be 500 times sine of, same thing, 25 degrees. So we just have to be careful to not confuse the angle from our bearing with the angle that we need to find sine and cosine. So we do 500 times cosine of 25, 500 times sine of 25, and what does that give us? That gives us these vector components, which tells us about this path that this plane is traveling. Okay, there we go. So what are we doing? We're going eastward at 453.1, and that is our miles per hour. And then we're going northward at 211.31 miles per hour. Okay. Now, next thing we're going to do is we're going to calculate the effect of wind velocity. So when we're in a plane, the wind can have an effect on us. So if we are headed due east, but there's a 65 mile per hour wind with a bearing of 60 degrees, and if we were assuming that with no wind, our speed is 450 miles per hour. Let's kind of sketch this one and see what we think about this. So, what are we doing? We are traveling due east. But we have this wind that is 65 miles per hour at a bearing of 60 degrees. So, let's see if I can get that in the right spot. Still not. There we go. Not quite 60, but we'll just go with it. So if this is 60, then I know this inside here is 30 degrees. All right, and then it tells us that assuming no wind, the speed is 450 miles per hour. So we will come back and sketch that in a second. So let's see, our AC is going to be this one. So if we start here with A and we go to C, we're going to have the wind. All right, so AC represents the wind. And that would be 65 times cosine of what? Well, if this is 60, then the angle with that horizontal axis would be 30 degrees. And then 65 times sine of 30 degrees. So AC in this case is going to represent the wind. Okay, AB represents, I'm going to let AB represent no wind and our speed being 450 miles per hour. So we're going to let AB be that. So this looks like this. It's 450 cosine of, I don't know, theta. And then 450 sine of theta. Okay, but when we add those together, we're going to get AD. AD is what's actually going on right now. This is headed due east. So we know that AD is what we get when we take the wind in and we add to that our speed, and then we get our final. So with this, what we have is a sum of these. 65 cosine of 30 plus 450 cosine of theta, and then 65 sine of 30 plus 450 sine of theta. Okay, now we know we are headed due east. So because of that, we know that this vertical component of AD, the vertical component of AD has to be 0. All of this vertical component equals 0 because I'm headed due east. I'm not headed north or south. So this is 0. So what I can do is I can take this part and set it equal to 0. Okay, and sine of 30, well, let's go ahead and solve for sine of theta. So what we would do to get sine of theta is we'd have to subtract this 65 sine of 30. Then we would have to divide by the 450. Okay, and so we can punch that in. We do know what sine of 30 is, but we can go ahead and punch that in. Negative 65 times sine of 30, close your parentheses, divide by 450. And what does that give us? When we do, whoops, not sure what that is, hold on. When we do inverse sine of that. This is approximately negative 4.14 degrees. Okay, so here's our picture up here. I'm going to go back and draw in this part here to get us there. Okay, so this is what we're solving for. We're solving for this angle here. So that negative 4.14 is this little part. So to get the bearing, to get our bearing here, I would take the 90 degrees and I'd actually have to add 4.14 to get that bearing. So that gives us a bearing of 94.14 degrees. All right, so we found that bearing. All right, now let's find the magnitude. So if we found the magnitude of AD, what is the magnitude of vector AD? So it's going to be the square root of our cosine plus 450 cosine of negative 4.14 squared plus, now this is the magnitude of AD, and that vertical component, because I'm headed due east, is 0. So what happens is this and this cancel, and the magnitude of AD is approximately 505.12. Now, what does that represent? What does the magnitude of that vector represent? Well, if we go back up and we look at our magnitude, it's going to represent our ground speed. So it's miles per hour, and this is our ground speed. So we have determined two things. We've determined the bearing, and we have determined the ground speed. Okay, so that's it for this lesson. You are welcome to also watch Mr. Campbell's if you like, and if you have questions, let me know.